Hi, and welcome to video 6.5, where we take a look at implementing object detection with SSDs and YOLO in Python using OpenCV. So now let's move into our IPython notebook with our lesson code. So I want you to open file number 20, SSD and YOLO object detection, OpenCV. I already have my file open, so I'm just going to take a look at it over here. So the first object detection model we're going to explore using is an SSD trained with MobileNet, and this was trained using TensorFlow object detector. Okay, so before I actually step through this code a bit, it's not super complicated, but it can be tricky if you're new to this. Let's just run the code and see how it works. So what we're going to do, we have different images here, different trial images here with the actual label on the image itself. But let's just take a look and see what our object detector picks up. All right, so this was the original image here, and this is the extracted image here. And this is what it actually picked up, elephant. So you can see the bounding box is pretty good. However, it probably should have covered the entire elephant here. But I'm not complaining. It actually got the animal 100% correct. Okay, so let's take a look at how it performs on some other images. So let's take a look at this traffic jam image I have. All right, so now let's take a look at this. So you can see it actually got almost all the cars in this image here, probably something that isn't a car over here. And it actually identified a traffic light accurately here. However, it missed this one here. That's not too bad. It's not too great either, but let's try it on some other images as well and take a look at performance on this one. So this is a laptop and a chair and a desk. It got laptop, it got keyboard, it got book in the end here. It got chair, which you can't really see because the keyboard is blocking the word, but it is chair here. So that's fairly good. I'm actually quite happy with that. Now let's try it on this one, which is a zebra and the giraffe, and it got both of them very correct. So that's awesome. Lastly, let's check out this one. Oh, apparently it didn't have the office image here, so I'm just going to delete that here. Add it into our data just in case you guys want to try it, but it's fine for now. So let's just leave it on zebra. We just run this code one more time, and there we go. So let's take a look at what's happening here with this code. How do we use this model that we're testing these images on? So I'm going to skip through some of this here. This is basically some image. If you noticed, all the images that outputted here were actually in this dimension. It actually cropped the images here. And that's because we have to feed the image into a specific size into this object detector, this trained object detector here. But for now, you can ignore this bit of code here. What this model here, this PB text file, points to a TensorFlow trained model, which is the SSD MobileNet version 1, trained on the Cocoa dataset. We have the frozen inference graph, which is actually the model weights as well. We have 90 classes, and we actually have a lookup here for the classes. So when we get a class in 0 or 1, it actually can use it to put text on the image so we know what we're identifying here. And what we do here, this is where we actually create our model here, our net model, using this read from TensorFlow function in OpenCV. So we have our weights, we have our PB text, which we defined here and here. We have our threshold setting. We have a flag that indicates whether the first and last channels in a 3-channel image is swapped. It's not super important, but actually it is important because if it's false, it's probably going to give you much worse accuracy because it's going to misinterpret the image. Then we have our blob, image blob from image here, which creates a 4-dimensional blob. And then this is what we use here to basically pull out our detections. So we have all of this stuff here just to get the image in the right format. And then what we do here, we basically check the boxes, make sure it's greater than the threshold here. And then what we do, we actually draw the rectangle over the image here, and then we get the class name by predicting, sending that box image here to get the text label. And then that's actually pretty much all it is in the end. So I should say detections are not done in here. The cycle iterated through here in this loop. Detections are generated from the blob over here as well. So you can take a look at this code. I may have brushed past some details, may have gotten a few things wrong because I'm trying to go through this quickly for you guys because this is more of a hands-on course as opposed to a theoretical detailed explanation of everything here. This is something quickly that you guys can use and adapt to your own application. So if you wanted to build, say, an object detector that detects a baseball bat in a video frame, what you can do, you can actually just look at this here, and every time it gets class, that was class 39, you can actually put a box over it and ignore all the other boxes it's doing, and you have your baseball bat detector. So that's quite cool. So now we've completed this little brief exercise here on using an SSD. Now let's take a look at YOLO. So the YOLO is pretty awesome, as I said before. This code I actually adapted from another project I saw on GitHub, and I added in a lot more comments too as well to help you explain it. Now this one as well, it's fairly simple, fairly straightforward. It follows a very similar format here as well, where we just get the weights, the config path from the YOLO. We have our images that we're going to test, so I'm going to loop through a few images in the directory I'm pointing to, which is images YOLO. And so those are some random test images I found. And then we actually just do the same thing here. We start timing the loop here just to see how it performs as well. We have all our confidences and class arrays and boxes defined above. We iterate through the different layer outputs, get the detections from here, and then we just plot things that are confidence over 0.5, which is what we regard as a fairly accurate classification. We plot here. We just draw the boxes lower down here as well, but we just get everything here. We apply some non-maximum suppression. That is basically so we don't get overlapping boxes. Okay, something I didn't talk about too much, but you can look this up. Non-maximum suppression is a technique used when you have many overlapping boxes to get the best box or the centered box in a way. And then, yeah, as I said, we just put the label on the image. So this is a fairly good project here. So let's take a look and try it out. Okay, so it got the elephant here, and it actually got a bird here. It's pretty cool. It's nice. Hot dog. Identify the hot dog 100% accurately. That is me, and yes, I am a person, and it's box over my entire body. And it actually got a boat in the background here, so that's awesome as well. This is the same desk area I had before. We have our laptop, we have our chair. It didn't get the books here, but that's okay. This is a living room setup. It got a clock, it got a potted plant over here. It got a vase here and a potted plant. That's actually pretty awesome. It got the sofa accurately. So you can already see YOLO is actually quite good. And this is actually an interesting one here. It actually got a truck. It kind of looks like a truck more than a car, like an SUV or a big van. This is a station wagon or SUV, got older version model SUV. It got all the cars on the road, the cars over here, traffic lights, both of them. So this is awesome. And again, it got the zebra and giraffe. You can't see the text too well, but it is giraffe. So you can actually put as many images as you want into this directory here, and just keep trying your YOLO detectors and see how well it performs. Alternatively, as a little homework lesson for you guys can set up this YOLO detector here to run on a video as well. Now you can see how slow the frame rate is here. However, it may actually work faster if you can do some sort of like algorithm where if there's not a significant change in the video screen, like if it's just like hovering on a scene of characters, you don't run classification here. I've developed that several times in some of my projects to speed up video classification. You only want to classify things when there has been a significant change on screen. So what I want you guys to do is adapt this code here, and maybe the code above too, whichever one you prefer, and adapt it to a video or a webcam stream. So that's going to be pretty cool. So this concludes this lesson here on applying and implementing object detectors, a YOLO and an SSD object detector in Python using OpenCV. Now let's just summarize what we've learned in this video. So in this video, we've learned how to load these pre-trained object detectors in OpenCV. We've experimented with SSD, mobile net trained, TensorFlow trained model, and a YOLO trained model as well, YOLO version 3. With this one with 90 classes, this one with 80 classes. And then we just applied those object detectors to several different images to assess their performance. Now let's move on to our final video, which is a quick fun video on neural art style transfer. So thank you.